16, right?
Yeah.
44 on page 329. Did we do 44? No, I don't recognize. I don't remember. I don't recognize it. Okay, very good. So 10 to the x, everything divided by x squared plus 1, x to the fourth plus 2. Now, let's analyze this problem first and identify a few things and then write it out.
Okay.
So first thing, any quantity that I see in the denominator will end up having a log with what sign in front?
Minus.
Clear, right? Okay. Now, there is no log of a sum. Remember, there are only three properties. Log applied to a product, log applied to a ratio, and log applied to a power. So if you ever see log of x plus 2, you cannot do anything to it.
Right.
Because there is no rule for log applied to a sum or a difference.
Right.
Okay. So I have to deal with the quotient, but since the numerator only has one term, one factor, then that's the only one that will have positive in front of the log.
Mhm.
Everything else, when you break it down, will have negative.
Mhm.
So how many factors in the denominator?
33.
Yes. So I'll have minus the first one, minus the second one, minus the third one.
Right.
So just observing that, it will cut the time in more than half.
Yeah.
Okay, so what will you do? What will you write?
You do log of 10 to the x
Yes?
minus log of the rest. Unless you want to break it up.
Yes.
Okay, so log x minus log x squared plus 1 minus log x to the fourth plus 2.
Notice no one can touch these. Why? Because we only have three properties. Log applied to a product, there is none. Log applied to a ratio, there is none. And log applied to a power, there is none. This is a sum. You can touch this, you cannot touch this, meaning there is nothing you can do here.
So I have a question. Why would you treat the never mind. That's it.
He always does that to me. Piques my attention and then
And then the first one will change to x times log 10. And then that's it.
I have to attempt, if possible, to simplify anything that does not have x in it.
Oh, okay.
There is nothing I can do here, 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 and there's nothing I can do to x.
Ah.
But every time I see a log in whatever base of a number, I have to ask myself,
So 10
10,
number
the
equals
base
10.
raised to which power is 10? 1.
Yeah.
So then this equals 1. So then the final
Becomes
simply,
x.
yes. So x minus log x minus log x squared plus 1 minus log x to the fourth plus 2. And this is it. Now, since we said, okay, let's also condense going backwards, I have a suggestion for you. What if we look at problem 69 on page 330? The title is Wealth Distribution. So I'm assuming it's because he's possibly Italian. Vilfredo Pareto observed that most of the wealth of a country is owned by a few members of the population. We know that already. So here it is. So he came up with Pareto's principle. Log P equals log C minus K log W. W is the wealth level, how much money a person has. Okay,
What is that? Log C minus
K.
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 Log W.
We'll see what it didn't say yet what K is. P is the number of people in the population having that much money. Okay. Okay, and later on they say something about P. Okay, solve the equation for P. Part A. Solve the equation for P. What would you recommend first?
So it's log of C over W to the K.
Yes. So you took the K because you realized that this is the product rule, the power rule. So this K comes from the power of W.
Yes.
And then you said, okay, there's a difference of two logs with the same base.
Yeah.
It must be log applied to a ratio. Awesome. That's the starting point. So log P equals, let's do it step by step, minus log W raised to K. Everyone agrees with this step? So then I write log P. So be very careful, this is an equation. An equation has one left side, one equal symbol, one right hand side. You cannot continue here and write equal symbol here. There would be a terrible mistake and I'll have to deal with it.
Okay.
Every equation has only one, is presented on one row. And you have to present the left hand side equal symbol and the right hand side. Okay. I don't want to sound mean, but I just want to explain why this is very important. If you continue writing here, then at some point in time you may lose track of which one is the left hand side or which one is the right hand side. You may consider that this is the left and that is the right. And that will collapse. It will not solve for anything. So that's why the equations have to be presented left equals symbol right. Nothing attached.
Okay.
And just write it one more time. Because once again, if you consider here, continuing with an equal symbol, then you may say, oh, this is the left, that's the right. And you're going to solve. Okay? Not because I want to sound mean or anything. Okay, so then the right hand side is log of C over W raised to K. Perfect. So what do I do next?
Use exponential.
Let's think for a second. You like to look? So, two numbers are equal, right?
Mm-hmm.
And they have the same log. What has to happen to these? Can I have here 5 and here 15?
No.
No. So two numbers are equal and they have the same log.
P equals C over.
However, Paul has a very good point. He said, and he thought of what I just said, that this is very important to remember that any log equation can be changed into an exponential, and any exponential can be changed into a log.
Right.
However, this is a log equation, but there is no need to change it into an exponential unless I have something like this on the number. Right? It's like, for example, I don't change this into a log.
Right.
There is no need. It's much simpler than that.
Yeah.
Meaning two numbers are equal and they have the same base. What has to happen?
K equals 3.
Right. The same thing here. Because it's a simpler situation than the one that requires changing it into an exponential. Here I don't have to do anything, I have to think. Two numbers are equal and their logs are the same. If the logs are not the same base, it's a totally different situation. But two numbers are equal, they have the same base, they have the same log, both sides, so these two numbers must be the same. But your point is well taken. So then P, we solve for P. P is C over W to K. Part B. Assume that k equals 2.1. Lowercase c is 8,000. And W is measured in millions of dollars. Fine. So W. Use part A to find the number of people who have 2 million or more. Okay. How many people have 10 million or more? Okay. So say it again.
Okay, no, I'm sorry.
Okay, so in y equals, c is 8,000 divided by, I'm going to put x to caret 2.1, come down, close the parenthesis, and then second and table. I have to go back to table set because this is changing all the time. Back to default. So second and table. So x, in other words, W is 2 million. Now I have to look carefully, where did this say? Okay, it doesn't say that it has to be in millions. So I have to put 2 million then. And press enter. And 10 million. 10 million. It says the wealth level. Find the number of people who have 2 million or more. How many people have 10 million or more? Okay. Let me see what I did. So it is x raised to 2.1, and we have c and p. I can have 2 times 10 to negative 10 number of people. So they just, in that case, they want us to just put the level. They don't want to put 2 million. Because I can. The answer makes no sense. So I'm just going to put 2 and 10. It doesn't say. Okay. But it makes no sense. Once I plugged in 2 million, I saw that the answer is 0.000000 people. It's obviously incorrect. So for 2 million, just the level. 2. So P of 2 is 1,866 people, and P of 10 is approximately 64 people. The point I'm making with this problem is just for you to see how many applications these functions have. Okay. Say it again. Yes, without the log.
I was saying, what if we use the log?
When?
I said, what if we use the log in the equation? Because wouldn't that force the domain to be greater than 0?
But
I mean, it's still greater than 0.
right. Yes. So C is a constant, so log applied to a constant, it's positive, it's 8,000. So this is W, which is a level in millions, 1, 2, 3, 4. It should have been clear from the problem, but it wasn't when we plugged in, although it does say level. So maybe I should have considered that. And K is a given constant, 2.1. So of course all these values are positive.
Yeah.
Is that what you meant to say, Paul?
Yeah, that's fine.
Okay. So 4.5, exponential and log equations. So let's start with exponential. Exponential equations. Okay. We already had some exposure to exponential equations. There are many different types, and a lot of them are a combination of exponential with something else. Now let's quickly review how many different types of equations we know. We know a lot.
Mhm.
Linear, rational, absolute value, radical,
Quadratic.
quadratic, polynomial. Did I say absolute value? I think I did.
Yeah. Sine.
Quadratic in form, trigonometric equations, awesome, trigonometric equations. And now this, and log equations. There are many different types, and I'm going to start with the simplest one, which we've already seen already. Here it is. I don't have to do anything. I don't have to change it into a log. I only have to think. I'm not simplifying. I'm not canceling anything. I'm just thinking. Two numbers are equal, and they have the same base.
Mhm.
So what has to happen? That's it. Okay, and now the next level up, I don't see it in the book. Here it is. A problem like this should be in the book. It isn't. Okay. So I'm looking at these two sides, and I say, okay, if I can present both sides with the same base, then the whole thing changes back into that,
Mhm.
the same concept. But I have to present both sides with the same base. I chose 1/8 and 32 so that I can present both with the same base. It is always wise to keep in the back of your mind, prime numbers. Even if you can use 4 or 9 or 6, it is recommended to think in terms of prime numbers as the base. Okay. So obviously 1/8 can be changed into 2 raised to. Very good. And then 32 can be changed into 2 to the
4.
16. That's 16.
Oh, 5.
Good. So then I'm going to copy the base on the left. And what happens to the exponents? Yes, very good. So 2 raised to
-6x plus
awesome, and 2 raised to
20x plus 15.
that's it. Now I'm really back to the first situation. Yes, it required some effort, but not a big deal. So then from here, what do I conclude?
-6x plus 3 equals 20x plus 15.
Yes. But just remember, we're not simplifying bases. We're not dividing bases. We're not doing any of that. We are thinking. Two numbers are equal and they have the same base. Therefore, -6x plus 3 must be the same with 20x plus 15. I subtract 20x. I subtract 3. So then x equals -12 divided by 26. And I will divide by 2. And that is it. Here's a question for you now. What did we decide about the exponential function? Is it a friendly function or not?
Yes.
Friendly. No headache, no restrictions, no problems. Awesome. I'll ask you that another question similar to that in shortly. Okay, on page 338. Problem 8. So we're moving away from easy, simple, or easy and simple, I would say, exponential equations. Now these are not trivial anymore. 3 raised to 2x minus 1 equals 5. But still not very difficult. So I'm looking at this. I know it's an exponential equation, and I know that the left-hand side has base 3, the right-hand side has base 5. There is no way I can present both with base 3 or both with the base 5 or both with any base. Okay. So here's the question, because I want you to relate to something we did in the past. So if I want to solve this equation, what is the idea? Well, the idea is to somehow remove this symbol. So what am I doing to both sides in order to remove this symbol?
Squaring both sides.
Why not cube? Right, and because the power 3 is not going to be the inverse operation of power 1/2.
Right.
So this is power 1/2. Power 3 will not help. Power 2 will eliminate that. Okay, so keep that in mind. That's the idea. Good. So now I'm looking at this equation and I say, I wish I had a mechanism similar to this one idea that will bring this power somehow down here and make it into a linear function. And there is only one function that does that. There is only one function on the planet that has that property. That if I apply it to both sides, it will allow me to bring the power in front as a number and factor.
Long.
Exactly. Does it matter which base? Base 10 or base E? No.
No.
It doesn't. So now I'm saying this. Two numbers are equal. Therefore, their log in the same base must be the same. Because this is a one-to-one function. If two numbers are equal and I apply the same log to them, the log has to be the same because the numbers are equal. So it's the exact reverse step that we had here. Here we said two logs are equal, they're in the same base, then the numbers have to be equal. Now I'm saying two numbers are equal, their logs must be the same. I need log because that is the only way to bring this in front, and if I forget to put parentheses, I mess up the entire problem. Because the power has to be a factor in front. If you omit parentheses, I'm not saying you will, but if you omit parentheses, you're only multiplying -1 by natural log. You're not multiplying this whole factor by natural log 3.
Does it matter which one?
As long as it's the same on both sides. Good. So then, remember natural log 3 is a fancy number. It's just a poor number. Natural log 5, just a simple, plain, poor number. It looks fantastic, but I'm going to divide both sides. Oops. I'm solving for x. What would be my next step? And that's it. I can do this. Or you can divide step by step. You can divide 1 by 2 and this by 2. Now, if you want, we can approximate it with the calculator, of course. So, in y equals, don't forget parentheses around the top, 1 plus natural log 5 divided by natural log 3 always close parentheses for the top, and then divide the whole thing by 2. I'm counting my parentheses, make sure I didn't miss anything. Yes. So the answer is 1.23 blah blah blah. So now how do I check my answer? What if I made a mistake?
You can plug it in.
Yes, here's how I plug it in. Let me show you how I plug it in. This is the original problem. 3 raised to 2x minus 1 minus 5 equals 0. It's the same thing if I check in 3 raised to 2x minus 1 equals 5, or in 3 2x minus 1 minus 5 equals 0. It's the same thing. The reason why I recommend you checking in this is because this 5 could have some power with x in it. And then if it does, when I'll show you how to check this, it will be so much easier. You don't have to evaluate twice. You don't have to set it equal to each other or check and so on and so forth. So I recommend do this. So here's how I check. So it was 3 caret in parentheses 2 multiplied by the previous answer minus 1. Close the parenthesis, go outside, minus 5, and when I click enter, what should I get?
0.
Yes, if this is the correct answer. If I don't get 0 something, I made an error somewhere. So enter. So therefore 1.23 is the correct answer. Now here is another type of exponential equation. To be exact, it's a combination. It's not an exponential equation per se. I would call it logistic equation more. Okay. I'm jumping to 26 and then I'll come back to the most difficult one. So 26. 10 divided by 1 plus e to negative x equals 2. Just for you. I'm sorry. Okay, so is this an exponential equation? Sort of, yes. Okay, so the an exponential equation has to have on one side a base and an exponent, and on the other side a number. Till I get it to that level or that stage, I cannot think of the steps that I would normally say, okay, let's do this or let's do that in an exponential. Not yet. So let's look at it before we look at this portion. We can say this is the exponential portion. I would have to agree. But before I look at that, I see something else. What do you see?
As a natural exponent.
Correct. So what I would like you now to not look at this, and tell me what you see before you look at that. What type of equation you see before you look at that little piece?
Rational.
Correct.
Mhm.
So now let's dig deep. How do I handle a rational? And what type of equation is this? Rational, specifically which type?
The denominator can be equal to 0.
Correct. Here's a hint for you. I would like you to be able to recognize this, because this is very important.
Proportion.
Exactly.
Wow.
So this is very important before. So that's why I'm trying to develop this skill with you.
Gotcha.
When you look at the equation first, I know that that's what the attraction is because that's what we are talking about right now. It's exponentials. But before I even look at that piece, I'll have to recognize that this is first a rational and it's a proportion, so I can handle it quickly.
Right.
Okay, so then what would you tell me to write?
E2 plus 2e.
Yes, but I would like to see it like this first. It's not a mistake. Equals Good. Here's why. Now you will recognize why I did not distribute yet. Because I can do what first?
So divide 2 on both sides.
Exactly.
Yeah.
Always remember, simplify factors, simplify factors. So yes, I will divide both sides by 2, and I have 1 plus e to the x equals
5.
right. Now, I hope you agree that this is way more human than the original one.
Yes.
So now it's very close to becoming an exponential, a pure exponential. I have one more step to go, which is?
Yeah, e to the negative x
Right.
minus 1.
Oh, I'm sorry. I have one more step to go.
Minus 1.
Exactly. So now I'll say, okay, now it's definitely exponential. It's definitely base e on one side and 4 on the other. I can't do any of that. So my only chance is to apply. Exactly. Why would I apply natural log in this case for sure and not log, common log? Because of the base e. So now this is clear. So remember the procedure. The procedure says if two numbers are equal, their logs have to be equal. And the left-hand side equals what? Yes, indeed. What about natural log e? What do we know about natural log e? Okay, we forgot. Here it is. Natural log e is a number that is unknown. But this is equivalent to, what is this base?
Base
E raised to which number is e?
1.
And we had a few minutes ago something very similar. What was it?
Yeah.
10 raised to 1 is 10. You can write it as a property if you want. Log base a of a is 1. Very good. So then the right-hand side is natural log 4. So finally x equals negative natural log 4, and you can approximate it if you want. Okay, now let's look at the what I think is the most difficult one. It's 23. Not difficult, I think, but it's long. 2 raised to 3x minus 1. Sorry, it's 3x plus 1 equals 3 raised to x minus 2. Since the left and the right cannot be presented with the same base no matter what you do, then the only chance I have to solve this equation is, does it matter which one? No, because this is base 2 and this is base 3, it doesn't matter. Okay, let's apply LOG this time. So remember, two numbers are equal, their logs have to be the same. Now tell me what you write on the left-hand side. Say it again. If I write it like this, it's wrong. Yes. Is that clear? Very good. Equals? Now, the reason why I say it's long, it's because normally this problem is asking us to determine an exact answer. You can say, oh, but I can plug this in the calculator and get 1 point blah, 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 and I can do this in the calculator, blah, 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 but that's not what we want. We want to solve for x as is, and then at the very end, plug the whole thing in the calculator once. So I will have to distribute. I will have to distribute this number to these two terms, this number to these two terms, move terms around, and solve for x. So 3x